In this video, we're going to calculate the area bounded by a curve and the y-axis. So we have already found areas bounded by a curve and the x-axis, and let's quickly review what's going on. When you have a region and you're trying to find its area using calculus, so let's say we are trying to find the area of this region. The idea behind what we're doing is we're splitting up the region into smaller pieces and adding up the areas of those pieces. So for instance, we are splitting up this area into little rectangles, okay? And then we're going to add up the areas of all of those rectangles. So we are adding up the areas of rectangles. And the area of each rectangle has a height and a base. Okay? In this picture, the height of my rectangle is the y value, or another way of saying that is f of x, y, which is some function of x. The base of the rectangle we're going to call delta x. Okay? So it's the y value, or f of x, times delta x. And while using actual rectangles may give us error, in order to get an exact answer, we're going to make our rectangles skinnier and skinnier and skinnier and have more and more and more of them. So we want an infinite number of rectangles so that the error disappears. Error meaning this little piece up here that I'm getting, or perhaps I'm drawing a rectangle here and I get a little extra. So when we say an infinite number of rectangles, or the number of rectangles approaches infinity, well, if that's happening, then the base of my rectangle is getting smaller and smaller and smaller, or delta x is approaching 0. So this becomes our integral. The area is the integral from whatever our starting x value is to whatever our finishing x value is of f of x dx. Our delta x becomes our dx in our integral, which is just a tiny little bit of x that is our base. When we have an infinite number, it's very, very, very infinitely small. Well, now let's think about how this works if we're finding area bounded by a curve and the y-axis. So let's say I have some curve here, and let's say that I'm trying to find the area bounded by the curve and the y-axis, and let's call our y values C and D. So I'm trying to find the area bounded by this curve, and the y-axis for y is C to D. Well, what we do, how we do that is very similar to how we do it for area bounded by a curve in the x-axis, except this time our rectangles are going to be sideways. They're going to look like this. Okay? And so I'm adding up my rectangles. My base, I'm going to call this edge my base, is a little piece of the y-axis, or delta y. Over here, the base was a little piece of the x-axis. over here, the base is a little piece of the y-axis. So each of these bases is some delta y, some little bit of y. And now the height, let's call this section here the height of my rectangle. Okay. The height of my rectangle, well, that's going to be an x value now. So remember over here, the height of the rectangle was a y value, right? This is a y value going up and down vertically. But here, this is an x value. Horizontal length is an x value. So my height is x, or we might call that some function of y. So in this case, my area is going to be the integral from c to d of f of y dy. So again, when we're finding area bounded by the curve and the x-axis, everything is in x's. When we're finding area and we're using sideways rectangles, area bounded by a curve and the y-axis, everything is written in y's. Okay, so let's try a problem. Let's find the area bounded by the y-axis and let's say, let's pick a nice function here. Let's say y is the square root of x for y from, let's go from 1 to 4. Okay. So let's draw a picture of this. We know that a square root function looks like this. Okay, so I'm going to get some specific values. When y is 1, x is also 1. 1 equals the square root of x. If I square both sides, I get 1 equals x. So that gives me the point 1, 1. When y is 4, well, what's x going to be? I'm going to square both sides, and I'm going to get 16 equals x. And so I'm going to have the point 16, 4. All right, so over here, that's probably going to be about from here to here. Okay, so let's draw a graph, a more precise graph. Okay, so I'll just kind of sketch in my curve here. There's my square root curve. So I'm going to start at the point 1, 1, and I'm going to go to the point 16, 4. So this is the part of the curve we're concerned with, and we want the region bounded from y is 1 to y is 4. So here's the region we're talking about. Okay. All right, so remember, when we're finding a height bounded by the y-axis, our rectangles are going to look like this. So we're adding up the areas of rectangles. The general formula is the integral from c to d of f of y dy. Okay. Well, c and d are my y limits. They are going to be 1 and 4. What is f of y? The function in terms of y. And again, remember, this, my height, that is going to be an x value. I want to know what x is, which is what we mean when we say f of y. So I'm going to go to my equation. Y is the square root of x. Well, what does that mean? That means that x is y squared, and that is f of y. So now I'm ready to set up my integral. Of course, the base of my rectangle is my dx, or I'm sorry, my dy, or delta y. So the area bounded by this curve in the y-axis is the integral from 1 to 4 of f of y is y squared, dy. That's going to be 1/3 y cubed when I integrate it from 1 to 4, or 1/3. 4 cubed is 64. 1 cubed is 1, which gives me 63 over 3, or my area is exactly 21 square units. All right, and that is how you find area of a region bounded by a curve and the y-axis for some y interval.